image, right? That is a function with respect to x and y. Suppose if you apply it to the Laplacian operator, right? Laplacian of Gaussian, that is what we call it as LOG. LOG is also a smoothing filter, right? But there is a typo here, right? Dou square f by dou x square plus dou square f by dou y square, not dou square y, right? It is a typo. It is dou square f by dou y square, right? We are partially derivating the function f with respect to x and y. That is a second order partial derivative equation. Right? Second order partial derivative equation, right? So what basically happen is we are measuring the um, point from the zero crossing of the Gaussian curve up to the peak, right? So that is what we call it as the del square G, right? And it will look like this. I hope this is that filter of LOG, right? LOG, Laplacian of Gaussian, right? And you might have seen that wherever there is a zero crossing, right, and up from the zero crossing to del square G, it measures the signal, right? So through which what is the primary objective? That you are measuring the entire image, right? Entire image's intensity distribution, the probability distribution of the entire image, right? What probability you are measuring? You are measuring the probability of the intensities, right? Probability of the intensity. That means you are modeling how the intensities are distributed across the image, right? Previously in Sobel-like filter, we will take only a static neighborhood of 3 cross 3 or 5 cross 5 like that, right? But in case of Gaussian derivatives, we will take the entire image. We will take the entire image and study how the intensity is distributed across the entire image. Okay.
Okay, sir.
And steerable filters. This is also a very important question for your CLA1. Steerable filters, right? So steerable filters are primarily used to detect contours. What do you mean by contours? Contours are connected pixels which are all having nearly equivalent intensities. Nearly equivalent intensities, right? Say for example, there will be one image, and in that image there will be some circular object, and that circular object will have nearly equivalent intensities across its border, right? Across its border it will have nearly equivalent intensities. So that we call it as contours. Contours are just like regions in the image, right? Under that particular region's borderline, that we specifically call it as contours, right? So for this, we use this Gaussian derivative filter, right, by taking the directional derivatives of the Gaussian function. Directional derivatives, right? So you can see f is the image and g is the Gaussian function, which is statically defined. And you see this u vector, right? This u vector represents the direction at which this particular image intensity moves, right? Say for example, this is uh, one gradient of a pixel, right? The Gaussian derivative of a pixel at location x. Okay, this is another one Gaussian derivative of the same pixel at y-axis, right? At y-axis this is, at x-axis this is, for the same pixel, right? Suppose if you want to orient these x and y towards u axis, u cap, then you will get this output. Okay, getting my point? So the same Gaussian derivative filter which we have studied in the previous, we have discussed in the previous slide, which can be used to detect contours by adding one more extra parameter that we call it as directional derivatives, right? And this
Okay, sir.
directional derivatives is represented using this u cap, right? And this, what is the use of this directional derivative? This directional derivative helps us to find the next pixel which is having the same intensity as similar to the current pixel. In which direction? Whether it is, there are 8 directions, right? If you concentrate on one pixel, there are 8 directions, right? There will be 8 axes. Either it can go this positive side or negative side or the top or bottom. In between there are 2 axes, right? I hope you know this, right? This is one pixel, right? Now we want to find in which direction the next pixel needs to be oriented. Oriented in the sense this pixel is having some intensity, right? In which direction which pixel is having the closest intensity as equal to this current pixel, right? It may be in this direction, maybe, right? Or it may be in this direction, or it may be in this direction, or it may be in this direction, it may be in this direction. Like this, there are 8 possible directions are here. This is a very, very important topic, right? Orientation. So we want to identify in which direction it is prevalent. Okay. So it is what you can use this with the help of these steerable filters, right? Steerable filters. Steering. Steering. What is the steering? What is the purpose of steering in car?
Changing the direction.
Exactly. Right. By identifying the direction, what we can find? Finally, we will identify the contours. Contours means connected regions. Once this pixel is connected to this pixel, and next we will apply, let us say this pixel is closely connected with this pixel, right? Next, what we will do, from this pixel we will identify the orientation, whether it will be connected this or this, like this 8 directions, right? Suppose if we connected here, then we will make, then it may connected here, then it may connected here, some direction, we don't know what may be the direction. Sometimes it may go downwards, like this, right? Finally you will get a contour, connected region, right? Like this we call it as a contour. Okay, clear?
Yes, sir.
Uh, what about others? Uh, I'm giving my full energy, man,
Yes, sir.
to make you to understand. It's none of my business, right? You may be knowing why I need to take class extra hours.
Sir, you could take some rest and you could come to class, sir, like online.
No,
You
no, I
have
planned
to.
to come like that, but what to do? Huh? I planned to take some rest from 6 to 7, but due to some urgent work, that to an official work.
Okay, sir.
Okay, sir.
Okay. So what filters are steerable, right? We have discussed, it turns out Gaussian derivatives. Gaussian derivatives of all orders are steerable within a finite number of basis functions, right? For example, a Gaussian second order derivative requires 3 basis functions. Second order derivative requires three basis functions, right? So what are all the 3 basis functions? Basis functions are also separable, right? So this is the order of 1, 2, and so on, right? That determines the value of m. Anyhow, it's not in your syllabus, but anyhow, you please know. And very important application of these Gaussian derivative filters is edge detection. Edge detection, right? So anyhow, we will discuss in detail in the coming chapter. At this point, you know the applications of Gaussian derivative filters. Okay, with varying sizes of filters. Like this might be 3 cross 5, this might be 5 cross 5, this might be 7 cross 7, or even 9 cross 9, whatever it may be, right? So if you take the Gaussian derivative filters of the same signal at a different scales, and finally you concatenate with and add a bias, right? Then you will get a um, reliable estimate of the edge. Okay. So integral images, right? If a diversity of box filters are to be employed, it can be very efficient to derive these from the integral image, right? Which is a 2D analog of a 1D cumulative sum. 2D analog of an 1D cumulative sum, right? That's what is also not in your syllabus, right? Integral images. Gaussian filter and Gaussian images are in your syllabus. That's very, very important, right? That you read. That is integral images, not recursive filters. Optimal linear, very, very advanced filter. Optimal linear filters. More research problems are in this still nowadays. We have optimal linear filters. It's all about linear filters, right? Basically, you concentrate on this Gaussian filters and steerable filters, right? Separable filters and steerable filters. Please understand the difference and how these borders are handled. That is also very important. Okay, and these point operations, right? Point operations, histogram, and this brightness contrast adjustment, inverse gamma, right? எல்லாம் கொஞ்சம் படிச்சு வச்சிங்க சரியா? Then coming to these non-linear filters, in many cases, many real-time problems, you might have seen that these linear filters are highly mathematical that will provide a more optimal result, right? You might have something like that, right? But actually, the fact is reverse, right? Linear filters are probably suboptimal. Suboptimal. That means it won't give you optimal output, right? Say for example, sort noise. Actually, in image processing and computer vision, what will happen is uh, the efficiency of the filters. Please listen carefully. Very, very important point, right? So the efficiency of the filters are learned or analyzed. How the performance of a filter is analyzed? They will have a clear image, right? Purposefully, some noise is added over the image. Purposefully, they will add some sort of noise over the image, right? And they will apply that filter, right? And try to recover the original image. This is what usually happens in case of filters, right? I'm repeating, very carefully listen. There will be an original image, clear image without any noise. Purposefully, some noise is induced. Different types of noises are there. Salt noise, salt pepper noise, right? Salt pepper noise, salt noise. Like this, there are so many noises are there, and those noises are overlaid on the image, right? And they will get an image with noise. Now they will apply the filter and try to remove the noises. Try to remove the noises. So after removal, they will study or analyze the quality of the image. If they got the exact quality as similar to the original, then they can say that the filter is highly optimal. If not, then the filter is suboptimal. Okay. One such example is given here, an original image in which they have added short noise. Short. Short means an abrupt change, right? In the pixel intensities. They will crack the image with some unwanted intensity values, right? That we call it as short noise, SHOT. And they will apply a linear filter, right? One such linear filter which they have applied is Gaussian low pass filter, right? Gaussian